Now I want to take a look at ways that you can use calculus and calculators to graph. Now, using calculators has never really been my favorite approach, but when the graphs get complicated enough, it is possible for the calculator to not be so much of a crutch, but to be a useful tool. So I'm going to run through an example here to show you basically the approach that I prefer for dealing with this type of problem. Let's say that our function f of x was equal to x to the sixth minus 10x to the fifth minus a 400x to the fourth plus 2500x to the third. All right. The problem with graphing this is the fact that you've got large powers and you've got large coefficients. Now, if you put that into your calculator, which I went ahead and did that, put into the y equal to, and just look at the typical zoom, the standard zoom, with those large coefficients and those large powers, you're not going to see a lot. With this one, we're only going to see like one vertical looking line, and that doesn't tell us much about the graph. Now, if you want to learn a little bit more about the graph, you can try things like, instead of just a standard zoom, you can do a zoom fit, which sometimes is a slight improvement. Now, we know that this thing is a sixth degree polynomial, all right? So and besides being a sixth degree polynomial, it has a positive leading coefficient. So we know from our end behavior, from our knowledge of end behaviors, that this thing will go off in an upward direction, all right, both at negative infinity and positive infinity, and that's not what we're seeing here, all right? So we're only seeing a small piece of the graph when we do things this way, all right? So here's my suggestion, all right? Here's a few tricks the calculator can help you with. I want to look at intervals of increase and decrease. That would be a helpful thing to know. The first derivative will help me with that. So f prime of x would be 6x to the fifth minus a 50x to the fourth minus a 1600x cubed plus a 7500x squared. Right now, what I need to do is find my critical numbers. In other words, I need to set this thing equal to 0 for critical numbers. And that is not something that I'm accustomed to solving just by hand. That's not something you just stick into the quadratic formula and get a solution for. Well, that's one place where the calculator could actually be of help. I'm going to hit the apps button, and I'm going to scroll down, and I'm trying to get down into the P's, into the apps that start with P. And the one I'm looking for is the Poly Simultaneous app, POLYSMLT. There's a second version of it there which does some things a little bit different, but this one will work. All right, so it gives me sort of an intro screen there, and I hit enter to get past it. And I'm going to go into my Poly Root Finder. And I'm dealing with a polynomial of degree 5 here, so I will tell it degree 5, hit enter. And then I start giving it my coefficients. 6 was the coefficient for the fifth degree. Negative 50 was for the fourth. Negative 1600 was for the third. 7500 was for the second, and the other two are non-existent. They're not there, so they're zeros. When I hit solve, and I hit solve by hitting the button right below where it said solve, it tells me that I've got zeros at x equals 0, got another one at x equals 0, repeated root. I've got a 0 at about 4.4. I've got a 0 at about negative 15, and I've got a 0 at about 18.93. Okay? So what I would do with that information, go back to the equal to screen. Well, better quit the root finder. Then I'll go to the equal to screen. I will not blacken that box in anymore so that it will ignore that. Put in the 6 x to the power 5 minus the 50 x to the power 4 minus the 1600 x to the power 3 plus the 7500 x squared. From there, I'll go to a table. So I'm going to look at my f prime number line, and the places I need to take a look are going to be around -15, around 0, around 4.4, and around an 18.93. All right, so on this table, I'll put in something like -20, and the thing that matters is that it is negative, so the function is decreasing. For this interval, I would put in maybe a -10, and it's positive, so that means here it's increasing. Between 0 and 4.4, I'll put in maybe a 3, and that's positive, which makes it increasing, which is the main thing we need to note. Between 4.4 and 18, I could put in like maybe a 10, and it's negative, so it's decreasing. All right, and beyond the 18.93, I could put in maybe a 30, and it's positive again, so it's increasing again. So what this has shown me, with a little bit of calculator help, is my intervals of decrease and increase, right? And beyond that, that tells me, since here I went from decreasing to increasing, that -15 is the approximate location of a local minimum. From increasing to increasing means at 0, nothing really happened, okay? From increasing to decreasing here, I have a local max, and from decreasing to increasing here, I have another local min. Again, those numbers aren't perfect, they're not exact, all right? But they give you some idea. I could go on to take my second derivative, and I'd get a 30x to the 4th minus a 200x cubed minus a 4800x squared plus a 15,000x, right? So what I would do with that, same thing basically, go back to my apps, back down to the Poly Simultaneous Solver, go back to the root finder. This time it's a degree 4 polynomial, and put in the 30 for the coefficient of the 4th degree, -200 for the coefficient of the 3rd, -4800 for the 2nd, 15,000 for the linear, and a 0 for the x. Hit solve. And this time, let's go ahead and draw the number line, save some trouble. I'm going to be looking at a 0, a 2.92, a -11, and a +15. So go back to the y = 2. Again, got to quit the root finder. Go back to the or equal to. Turn off the first derivative and enter in the second. 30x to the power 4 minus 200x to the power 3 minus 4800x to the power 2 plus 15,000x. So there's the x. All right. And now when you look at your table, it's the y3 that you're going to be seeing. And you can go back to doing it the same way we did before. And I need to make that a 15,000 instead of a 1,500. All right. And so I could put in a -20 negative 20. And that positive tells me that this part's concave up. Put in a negative 5. This negative, I'm getting a negative on my screen, which is telling me it's concave down. Putting in a 1 tells me it's up again. Putting in a 10 tells me it's down again. Putting in a 20 tells me it's up again. So I've got my intervals of concavity up, down, and points of inflection at approximately, not exactly, not perfectly, but at these approximate values, I have points of inflection. So with that, the calculator can actually render some useful aid in approximating the graph of a polynomial.